Okay, so in this first video, I want to take a moment to discuss a little bit about the what and the why to programming. So what exactly is programming and why do we actually do it? So to get started, we'll first address that question, what exactly is programming? So this is going to be the process of developing a software application. So it's going through the essentially going through the motions of writing or, as programmers would say, implementing your software based on some kind of design you've come up with. In order to come up with this design, that usually involves either being given some directions or kind of figuring out what those directions are going to be on your own. They're generally going to be problem statements, maybe user requirements that tell you what it is that you need to be designing, what it is that you'll need to eventually be implementing. Once you've actually built your software, you then want to make sure that it actually works properly. So that also involves some amount of testing, debugging, or troubleshooting. And then once you've got it all working the way you want it to, then you actually deploy it. So that's the part where you actually try to sell your idea. So the primary part that we're going to be focusing on is going to be the implementation part. So that's the part that we would typically describe as the programming. So everything else that surrounds this idea, usually you would refer to all of that together as software engineering, which is a slightly more advanced way of describing programming, something that you can go ahead and save for a little bit later. So when we talk about programming, actually writing out some code for a program, the way that we could typically describe this is that it's both an art and a science. So there's going to be this subjective nature to designing your program. If you're given something very complex, then there are many different ways you can go about solving that particular problem. And the exact way that you decide to go about it really kind of depends on the trade-offs that you're willing to make. You know, are you going to make your code more readable at the expense of maybe making it less efficient? Are you more concerned with the way that the user interface looks and the way that it feels as opposed to maybe how fast it happens to be? So there's many different things you have to consider there. There's also some consideration for when I talk about readability, how presentable your code actually is, where if you were to take that piece of code that you've written and you were to look at it, you know, is it something that you could actually stand to look at for a long period of time, or does it just hurt your eyes? So there's some consideration to the general style of the code that you're writing. And I'll talk a little bit more about style, what that means, and some of the characteristics of style a little bit later. The other side of this, when we say that it's a science, there's also going to be the subjective nature to actually analyzing and testing your program. So when I talk about these different trade-offs that you have to consider, obviously the amount of weight that you put to each one of these trade-offs, which ones you're going to prioritize, that's somewhat subjective. But when you go about measuring those trade-offs, when you say, okay, this is how fast my program is, or this is how many lines of code my program happens to be, that's very set in stone and very objective part to programming. So that comes with the process of analyzing and testing your program. You know, there's either going to be, when it comes to testing, there's either going to be a right way for the program to work or a wrong way for the program to work. So summarizing these points right here, so we would say that our programs are designed so that both the source code and the application itself can be easily understood by other people. So how well somebody can understand it or how intuitive it is generally going to be the most important part. And then there's also going to be, on the more objective side, there's going to be syntactical rules. So there's a syntax that you have to follow for building, analyzing, and testing your programs. And these syntactical rules are very strict. So if you misspell a word, or if you capitalize a letter in a word where it wasn't supposed to be capitalized, your program's not going to work. So it's very, very strict about this. And you have to adhere to the rules of this programming language you use at all times. Also, for anybody that's curious, the graphic that I've included with this slide, if you want to see more of this kind of design, these are recursive binary trees, or recursive tree graphics. In this particular case, this one's treated as a binary. When you get to the end of Fundamentals 2, so about a year from now, you'll get to see a little bit more of this. Alright, so now that we've addressed a little bit about what programming is, now I'm going to take a moment to address a couple of different questions about why it is that we write programs. So the 4 questions I've laid out here, we've got what is the purpose of writing programs, what are the benefits of writing good programs, what are the consequences of writing bad programs, and why do we need programmers? So the purpose of writing programs, for most people that seems pretty obvious. The reason that we write programs is because of the fact that they make our lives much easier. So they help us with automating various tasks. Typically, the primary purpose that we have computers is that they can do all of the different kinds of calculations that we can't. And the reason that we still exist, even though we have all these computers, is because we can do all the things that a computer can't do very well. So to give you an example of this, a computer is very good at crunching numbers. They're very fast when it comes to any kind of math problem, whereas a person is better when it comes to things like pattern matching or more intuitive-based knowledge. So like, say, if you're trying to look at a picture and determine what the contents of that picture are, currently people tend to be much better at that than computers. We're slowly improving the quality of computers there, but it's still going to be some time before that's nearly as good as a human is. Then, of course, the question, what are the benefits of writing good programs? So naturally, of course, that kind of feeds into the purpose of writing programs in general. If you write a good program, this is going to be something that people actually enjoy using. If you're thinking about this financially, it's much more marketable if you have a good program than a bad one. These tend to be the ones that stick around the longest, so they are well understood. As a programmer, you could also say that they're well documented, so understanding how to actually maybe make some adjustments to that program, that tends to have a lot of, there's a lot of writing about that as well. When it comes to the consequences of bad programs, so these tend to be things that have clunky interfaces, they're very hard to understand or to use. They are slow, or they consume a lot of memory on your computer program or your computer. In the worst case scenario, since we're primarily talking about security, bad programs can lead to leaking your private information. They can, in the worst case scenarios, depending on what the programs are written for, they can also lead to things like bodily harm, loss of life. Some of the issues that you run into, say for example when you're dealing with smart cars, is a more recent example. When the programs for those are written poorly, the worst case scenario is that somebody loses their life. So it's very important when we consider the consequences of writing bad programs that we be very careful about precisely how we wrote them, and we make sure that they are as secure as possible and that we've thoroughly tested them. So why do we need programmers? Well, the primary reason that we need programmers is to make sure that we're writing good programs and not bad programs. And the funny thing about programming is that, or software engineering in general, is that unlike other engineering disciplines, it's very cheap to become a programmer. If you think of something like, say, a civil engineer, there's a lot of materials that they would need, very expensive. But when it comes to being a software engineer, all you really need is a computer and any free piece of software to start writing code, and you're pretty much off. So because of that, it's very important to make sure that the people who are actually writing the majority of programs out there actually know what it is that they're doing. So then kind of a follow-up question for this is why it is that you might want to become a programmer. This will primarily be directed at the people that are in this course in the pursuit of a computer science degree. If you're in computer information systems, maybe this question isn't as much of a concern for you. In my case, the reason that I wanted to be a programmer is because I wanted to be able to provide people with the tools that they need so that they can achieve success, which is primarily also why it is that I'm involved in teaching, since it's kind of the same general idea. Okay, so now we'll look into different kinds of programming. So a couple of different problem domains that we might consider include things like application software, web development, game development, automation, data science, embedded systems, machine learning, and operating systems. And for each one of these different domains, there are a couple of different languages that we could choose from. So say, for example, with application software, there are languages such as Java, which we'll be using in this course. There's also going to be languages like C, Python, JavaScript. Primarily, you're going to use JavaScript for web development. So there's a little bit of application software using specific frameworks with JavaScript. In web development, you've got JavaScript, Python, Java, and PHP. With game development, typically with game development, you're looking for languages that are both fast and don't take up a lot of memory because you're trying to compact so much data in a gaming application. So typically you're going to be using C++ and C#, but some alternatives include things like Java and Python. With automation, in that particular area, Python kind of reigns supreme. Java kind of trails behind that a fair bit. With data science, again, this is another domain where Python is the big winner, but other languages include things like R, C, and Java. With embedded systems, this is similar to game development in that you're really looking for languages that are fast and don't consume a lot of memory. So C and C++ will be the dominant languages here, but we also have Java and Python. Machine learning, this is another one where Python is clearly ahead of everything else, but we also have things like C++, Java, and JavaScript. And then for operating systems, this again is similar to game development and embedded systems. So you're primarily looking for, in this case, you have languages that are described as being closer to the hardware. So the two primary ones you see are C and Objective-C. C is the language used for the Windows operating system, and Objective-C is the language used for Mac OS. So putting this all together in a slightly different way, this is a map of all of the different domains you might consider for computer science. So this is a bit more developed or a bit more fleshed out than just this list of items that are provided here. If you want to try to navigate through this to see all the different areas you could pick from, go ahead. Okay, so now that we've considered a little bit about the different areas of programming, we understand a little bit about the what and why. Now we'll talk a little bit about how programs are actually written. So whatever you're writing a computer program, there are going to be 5 elements that you should consider. These include the syntax, so those rules that I mentioned before. There's going to be keywords, operators, punctuation, and programmer-defined names. So the syntax is going to be the set of rules that dictates how the elements of a program must be structured. That's going to include things like the usage and placement of keywords, as well as operators, punctuation, and those programmer-defined names. So essentially the syntax, you can think of this kind of like the grammar and the spelling of a spoken and written language, very similar. So to give you a few examples of pretty standard rules or standard grammatical rules, sentences will start with a capital letter and they end with a period. And then all of your words and punctuation marks need to be placed in a specific order. So if you're going to speak a sentence or write out a sentence, there's a particular order that the words have to be placed in. Otherwise, it just comes out as just complete gibberish. And this is also true for your punctuation marks. So when you have things like periods, commas, maybe semicolons, quotation marks, all of those have a particular place where they need to go. So then we get into keywords. So this is going to be something that's a bit more unique to programming. So keywords are special words that are reserved by the programming language. They have a special meaning and they serve a specific purpose in your programs. So to give you a quick list of all of the keywords that Java includes. We've got this little table right here. I will go ahead and say now, you don't have to worry about knowing all of these. In fact, you only really are going to need to know a couple of these when we first get started, and we'll slowly add a couple more. You're only really going to end up knowing about roughly half of these by the end of the semester, and we'll add another little bit by the end of Fundamentals 2. So you don't have to worry too much about trying to know all of this all at once. We'll slowly work our way through this table. For operators, so these are going to be used to perform operations on operands. So you can think of this kind of like with math. The operands are going to be items of data, typically numbers. For example, you're probably familiar with most of the operators in math, such as addition. So we've got an example here. We have 5 plus 6. So the plus symbol is the operator for addition, and then the two numbers are going to be the operands. So 5 is the first operand, and 6 is the second operand. Our punctuation, similar to our keywords, that's going to be part of the syntax of the language, and most of the punctuation marks have a special meaning and purpose. For example, in most programming languages, but not all of them, Java will be one of them that does include this rule. Your statements are going to be ended with a semicolon. So in much the same way that you would end a sentence in a spoken and written language with a period, or at least most spoken and written languages, all of the statements in Java will end with a semicolon. So we've added that here with 5 plus 6, and then that semicolon to show that that's the end of that statement. But I will note that what we've shown right here is not actually a complete statement. There's a little bit extra that we need to add to it. So programmer-defined names, these are going to be any other words that we use in our program. So this is basically everything else besides the keywords. These are going to be things that are not reserved by the language itself, but are instead going to be defined by the programmer, as the name would imply, programmer-defined. Each language does at least have some syntactical rules for how we can write those programmer-defined names. Additionally, if this doesn't seem obvious already, we cannot use any keywords as programmer-defined names. Before we learn about those different rules, though, I'm going to go ahead and just give you a simple case. This will be with a programmer-defined name that does follow those rules, even if we haven't seen what they are yet. So variables in programs will hold data, such as the results of a mathematical calculation. Since this data can come from many different sources, it's millions and millions of different ways that we might collect some data. We need to make sure that the programmer gets to decide what they're going to call those variables that will hold that data. Because if the programming language got to decide that for you, you would be very restricted in what you could name your variables, which is both confusing and also very limiting. So the variable names are going to have to be decided by the programmer. So let's go ahead and include a variable. So we've got a variable name here that's going to hold the result of adding the numbers 5 and 6 together. And so because 5 plus 6, adding two numbers together, that's a sum, the variable name that I've chosen is going to be sum. So the variable sum is going to hold the result. So 5 plus 6, it's going to hold the value 11 in it. Another operator that I've included with this statement here, so that now it essentially is a complete statement, is that equal sign. That is going to be the assignment operator. As we learn a little bit more about variables, which we'll expand on with the next section after this, you'll be able to better understand the purpose and usage of that assignment operator. Okay. So at this point, this is going to complete everything for this first section. Going into the next one, we'll kind of expand upon this idea of being able to write statements. Primarily what I'm going to focus on, if we look at this example, we're going to focus a little bit on assignments, and we're also going to focus on something else that we need to do with our variables, which is declaring them.